In problems like this one, and if you remember problem 4e, where you're given a relationship between the output y and the input x, it's very easy to find the Fourier transform H(e⁻j⍵) directly without ever having to know h of n. So we don't need this, we can directly arrive at this. How do we do this? We look at the original equation and then we try to take the Fourier transform of both the sides. So for this equation, the left side of the equation transforms to y(e⁻j⍵). For the right hand side, you have a constant, then a summation, again both of which are independent of the DFT is independent of both of them, so it's 1 over n sum over k going from 0 to n minus 1, as you know, as it is. What's the DTFT of x of n minus k? So if the DTFT of x of n was x(e⁻j⍵), this is a shift by k. So the DTFT of x of n minus k should be x(e⁻j⍵) e⁻j⍵k, right? So the DTFT of this term is x(e⁻j⍵) e⁻j⍵k. Since this is not a function of omega, we move it out of the sum and we get 1 over n x(e⁻j⍵) sum over k going from 0 to n minus 1 e⁻j⍵k. We have been asked for a closed form, so we need to solve this, and we remember that sum of k going from 0 to a r to the k is 1 minus r to the a plus 1 over 1 minus r. So this becomes 1 over n x(e⁻j⍵) 1 minus e⁻j⍵, because that's what your r is. Your r is this, r to the power n plus 1, that's capital N, over 1 minus r. So now we have y(e⁻j⍵) in terms of x(e⁻j⍵) and some other function of omega. But if you remember the relationship between y and x, y is the convolution of x and h, therefore the Fourier transforms were just a product, and from here we get the system transfer function. The Fourier transform is the output transfer function over the input transfer function, something you remember from controls or linear systems. So from here we get y(e⁻j⍵), this going to the denominator, x(e⁻j⍵), that forms your Fourier transform, which would simply be 1 over n 1 minus e⁻j⍵n over 1 minus e⁻ j⍵. So we directly arrived at the system Fourier transform without ever having to find h of n. Although that could have been done for this problem, we didn't have to. Problem 4e, if you remember, was y of n was simply, this is problem 4e, x of n plus 1 plus x of n minus 1. if you took the Fourier transform of both sides, you would have got y e to the j omega is x e to the j omega. Since it's a shift of +1, e to the plus j omega, plus another one of these times e to the negative j omega, which would have given us the system transfer function as just this, which is 2 times cosine omega. Well, this is exactly what we wrote at that time. Which is also this. We are further asked the magnitude and phase of this frequency response. Now it's there are several, like, 2 ways to do this. You can decompose an exponent as a cosine plus a sine. Do it both here and here. Find the real part and the imaginary component, and then do the magnitude thing. But a better method would just be doing this. If you remember, we convert this into a sine by multiplying and dividing by half of that. So we do e to the plus j omega n over 2, e to the minus j omega n over 2. Right, so we are not really changing anything because this is 1. Here, half of that is e to the plus j omega over 2 times e to the negative j omega over 2. Using this here and using this here, we get 1 over n e to the j omega n over 2 e to the minus j omega n over 2 over e to the j omega over 2 minus e to the minus j omega over 2. You can see that these two form sinusoids as 1 over n sine omega n over 2. The 2 j's would cancel out, over sine omega over 2. So we have not yet accounted for this portion. We only use this up here, so this needs to be here and here. So this ends up being e to the j omega n plus 1 over 2, e to the negative j omega n plus 1 over 2. So the magnitude can be written as simply the absolute value of this, and the phase is going to be negative omega n plus 1 over 2. Now this is only half of the phase. You remember to do this plus pi times u of minus what's the real part of this? Just um, you can simply write real part of that, and to make it an odd function you can multiply it with sine omega. In part C we are asked for an efficient difference equation for y of n. The equation for y of n that we know is y of n equals sum over k going from 0 to n minus 1 x of n minus k, 1 over n x of n minus k. How about y of n plus 1? Let's try to write that. That's going to be 1 over n. Now that's the capital N, it doesn't change. Sum over k going from 0 to n minus 1 x of, here n becomes an n plus 1 minus k. What this means is the original sequence was simply starting at k equals 0, it was x of n plus x of n minus 1 and so on up to x of n minus n plus 1. This new sequence is starting at k equals 0, it's x of n plus 1 plus x of n plus x of n minus 1 up to x of n minus n plus 2. That's actually the term before this one, the x. If you plug in n minus 2 for k, you get x of n minus n plus 2. So what we have here is this portion, and this was our y of n. So I can say this is equal to x of n plus 1 plus this whole portion is y of n minus this, right? This excess subtracted from y of n is this, and this is also here, so it's y of n minus x of n minus n plus 1. So now we have a difference equation. Y of n plus 1 equals y of n plus x of n plus 1 minus x of n minus n plus 1. And since it's the convention to write y of n in terms of y of n minus 1 and so and so, we can simply rearrange the terms, move this to the left, you get y of n equals x of n plus 1 minus x of n minus n plus 1 minus no, we shouldn't be doing this, I'm sorry. So since the convention to write a difference equation is to write y of n in terms of yn minus 1 and so on. We will need to replace n with n minus 1 everywhere. So we get y of n equals y of n minus 1 plus x of n plus 1 minus x of n minus n plus 1. This is our difference equation for y. And this is so much more efficient than this. So here we were having a total of n multiplies to calculate a single value of yn, or even here there were n multiplications going on, or n, maybe not a multiplication but n additions. Here it's just the previous term plus 2 more terms. So this is very efficient.